Hey you guys, Mrs. Nzlako here. I am going to read out loud to you the review book portion of your final assignment for your Earth Science class. And that is to read pages 64 to 75 and answer some review book questions. As I read, I'm going to be underlining important information and making text annotations. Page 65, sorry. Actual Earth motions. Earth moves constantly in a variety of motions. Earth moves with the Milky Way galaxy as the universe expands. It moves around the center of the Milky Way galaxy with our solar system in a 225 million year period. Earth also rotates and revolves around the sun in an orbit. Rotation of Earth. The spinning of Earth is on its axis, the imaginary line through the planet from the North Pole to the South Pole is its rotation. The axis of Earth is titled 23.5 degrees from a line perpendicular to the plane of its orbit of the Sun. As Earth orbits the Sun, Earth's axis remains tilted at 23.5 degrees. The north end of the axis points towards the North Star or Polaris. Earth rotates 360 degrees from west to east in 24 hours at an angular rate of 15 degrees per hour. This angular rate is the same at all locations on Earth. Looking down over the North Pole, the direction of Earth's rotation is west to east, counterclockwise, as shown in Figure 4.7.
Hi, Mommy.
Evidence of Earth's rotation. Throughout much of human history, scientists have searched for evidence that Earth rotates. Earth's movement is not apparent because people don't feel very smooth motions the same way that they are aware of abrupt motions. Also, there is nothing near Earth with which to compare its motion. Only in recent history have people and satellites been able to observe the rotation of Earth. The Foucault pendulum. When a Foucault pendulum its path is allowed to swing freely, first observed in 1851, its path will appear to change in a predictable way, as shown in Figure 4.8. This is evidence of Earth's rotation because of the pendulum, due to inertia, would continue to swing in the original path if Earth did not rotate. The path of the Foucault pendulum only appears to change. Actually, the pendulum swings in a fixed direction in space, while Earth, carrying the observer with it, rotates under the pendulum. If you could observe the pendulum moving through a powerful telescope in space, you would see no apparent change in its path. Foucault pendulums can be found in a number of museums to recreate the experiment. The Coriolis effect. The tendency of all particles of matter moving at Earth's surface to be deflected or curve away from a straight line path is the Coriolis effect. The deflation is to the right in the northern hemisphere and to the left in the southern hemisphere. This deflection occurs because Earth is rotating, and therefore Earth's surface is moving with respect to the path of the particles. The following example can help to explain the effect. Imagine that you are at the center of a merry-go-round that is rotating counterclockwise. Your friend is near the rim of the merry-go-round. You throw a ball directly at your friend. By the time the ball reaches the rim of the merry-go-round, your friend has been carried to the left. The ball reaches the rim at a point that is now to the right of your friend. With respect to the moving merry-go-round, the ball has been deflected to the right. In a similar manner, rockets, ocean currents, large storms, and winds are deflected with respect to Earth's surface, since the only reasonable explanation of the Coriolis effect is that Earth rotates. The Coriolis effect is good evidence for Earth's rotation. Evidence of Earth's revolution around the Sun. Earth revolves around the Sun in a slightly eccentric elliptical orbit or path once a year. Earth revolves in a counterclockwise direction. So I'm just going to make a little memo over here. Which way is counterclockwise? As viewed from Polaris, at a rate of approximately 1 degree per day, 360 degrees in 365 days. Just as scientists had trouble proof of the Earth rotates, they also had difficulty finding the solid evidence of Earth's revolution around the sun. If you understand the Earth's limited change in distance from the sun during the year does not cause seasons, then the seasonal changes associated with changes of the sun's path is evidence of the revolution. If Earth did not revolve around the sun, the same part of Earth would tilt toward the sun all the time. Therefore, the same part of the Earth would receive more direct rays of sunlight. The seasons would not change. Each part of Earth would have the same season all the time. So seasonal changes justify that the Earth revolves. Having different constellations associated with each of the 4 seasons is further evidence of Earth's revolution. A constellation is a group of stars that form a pattern and are used to help people locate celestial objects. At night, you can see different constellations at different times of night. Earth's revolution around the sun produces other effects that can be used as evidence of revolution. During the year, the apparent diameter of the sun changes in a cyclic fashion. Earth's changing distance from the sun as Earth revolves in a slightly elliptical orbit causes the size of the sun to appear to change. The sun appears the largest when the Earth is closest to the sun, around January 3rd. The sun appears the smallest when it is farthest away from Earth, on about July 4th. Slight changes in the Doppler effect of stars can also be used as evidence of revolution. As Earth revolves around the sun, Earth is traveling toward a given star for about half the year, and the other half of the year it is moving. Away from a given star. These movements toward or away from a star result in a small yearly cyclic changes in blue and red shifting of starlight. Review question number 23. The Foucault pendulum provides evidence of Earth's rotation, revolution, insolation, or inclination. Number 24. On Earth, surface ocean currents rotate clockwise in the northern hemisphere and counterclockwise in the southern hemisphere because of the 1. Coriolis effect, 2. Seasonal effect, 3. Tidal effect, or 4. Doppler effect. Earth and moon motions and time. Throughout the ages, most cultures have used the actual motions of Earth and or the moon as a frame of reference to determine time. The concept of the month is based on the length of one cycle of our moon's phases. The day is based on one rotation of Earth as measured by apparent motions of the sun. The year is based on one revolution of Earth around the sun as measured by changes in apparent motions of the sun and other stars. Specific time within a day more difficult to determine. Local time. Time based on the rotation of the Earth as reflected in motions of the sun is called local time. All places on the same north-south line or meridian of longitude have the same local time. However, locations even slightly east or west of any meridian have different local times due to Earth's rotation. There are 2 types of time based on observations of the sun at a single location. So, time is either local, solar, or time zone standard. For any location, the sun reaches its highest point in the sky once each day at solar noon. This time it takes for the Earth to rotate from solar noon to solar noon on 2 successive days at any fixed location on Earth is the solar day. This type of local time based on the motions of the sun in the sky is solar time. Apparent solar time or sundial time, because of sundial, is used to measure it. If Earth moved around the sun in a circular orbit at a constant speed, the apparent solar day would have a constant length. However, Earth's speed around the sun varies in a cyclical manner in the course of the year. As a result, the length of the apparent solar day also varies during the year. Days of varying length make it very difficult to measure time using clocks and watches. Therefore, For convenience in timekeeping, a solar day of average length, the mean solar day, has been established. The second type of local time is mean solar time, which is based on the mean solar day. It has been divided into exactly 24 hours. On most days of the year, the solar day is either slightly more or slightly less than 24 hours in length. Time zone or standard time. Time zones have been created to standardize time for regions. Because there is no limit to the number of meridians of longitude that could exist, there could be a different local time for each meter on kilometer where you live. To solve this problem, 24 separate time zones in 15-degree wide east to west bands have been established. All parts of Earth within each of these 15-degree longitudinal bands maintain the same time, as shown in figure 411.
Mommy.
Yeah, Jojo.
How many do this take?
Since Earth rotates 360 degrees in a 24-hour period, each 15-degree band has a difference of 1 hour in time. Each time zone keeps the local mean solar time of the meridian that is in the middle of the particular time zone.
I'm almost done.
I'm almost done. Number 29. If Earth's rate of rotation decreased, there would be an increase in the length of the seasons, sun's angle of inclination at noon, number of observable stars seen at night during the year, or length of an Earth day. How long does Earth take to complete one orbit around the sun? 1 day, 1 month, 1 year, or 1 decade?
Hey, Mommy.
Number 34.
Mommy.
Yeah, Jojo.
I have my pen and put it right there. Open it.
Sorry, Jojo. Open it? Okay.
Why do you
Number 34. When does local solar noon always occur for an observer in New York State? 1. When the clock reads 12 noon.
Mommy, why do you close it?
I didn't close it. I opened it because you asked me to.
Why do you close it?
When the clock reads 12 noon, when the sun reaches its maximum altitude, when the sun is directly overhead, or when the sun is on its prime meridian. Number 39. What is the time in San Francisco when it is 6 a.m. in Dallas? 5 a.m., 7 a.m., 3 a.m., or 4 a.m.? Actual motions of Earth's moon. The revolution of the moon around Earth as Earth revolves around the sun results in many common observable events, including phases of the moon, tides, and eclipses. The moon revolves around Earth in an elliptical orbit that is tilted about 5 degrees from Earth's orbit and has a period of 27 1/3 days. Besides revolving around Earth in 27 1/3 days, the moon also rotates on an axis in 27 1/3 days. Thus, as the moon revolves once, it rotates once. This is the reason why the same face or side of the moon always points toward Earth. Figure 412 provides some details in the orbital motions of Earth and its moon. Moon phases. Half of the moon is always receiving light from the sun at any given time, except during lunar eclipses. Since the moon revolves around Earth, an observer on Earth sees varying amounts of light of this lighted half as the moon moves throughout its orbit. The varying amounts of lighted moon as seen from Earth are known as the moon's phases. Because the revolution of the moon around the center of the Earth-Moon system is cyclic, the phases of the moon are also cyclic. However, because of the revolution of the Earth-Moon system around the sun, the cycle of phases is somewhat longer than the time of one revolution of the moon. The period from one full moon to the next is 29.5 days, whereas the moon's period of revolution and rotation is just 27 1/3 days. The difference in time is explained in figure 414. Tides. The gravitation between Earth, the moon, and the sun results in a cyclic rise and fall of ocean waters on Earth called tides. Figure 4.5 illustrates a typical tide pattern and how the varying positions of Earth, the Moon, and the Sun result in different levels of ocean water. The tidal effect is caused primarily by the Moon, not the Sun. Even though the Moon is much smaller than the Sun, it is about 400 times closer to the Earth. Figure 4.15 illustrates that there is a bulge of water, high tide, on Earth directly under the Moon's position. There is also a high tide on the opposite side of Earth because the solid Earth is closer to the Earth-Moon center of gravitation than the ocean water. This causes Earth to be pulled away from the water, leaving the high tide at right angles to the positions of high tide, and gravitational pull of the Moon is least and the levels of ocean water are low, resulting in low tide. Because Earth is rotating, the low and high tides follow the straight line alignment between Earth and Moon. The timing of high and low tides is not only affected by the rotating Earth, it is also influenced by the Moon revolving around Earth. Thus, the ideal time between two high tides or two low tides would be about 12 hours and 25 minutes. A complete ideal cycle of two high tides and two low tides at a location would then take about 24 hours and 50 minutes. Few ocean shores experience an ideal cycle of tides due to many factors. The effect of the Sun on tides is largely that the reducing or enhancing their heights. When Earth, the Moon, and the Sun are in a straight line, the Sun enhances the tidal effect. Yeah, Jojo. This large tidal range happens during new and full moon phases. When the moon is one of the quarter phases, the Sun is pulling at right angles to the moon. As a result, high tides are then lower and low tides are higher, producing a smaller tidal effect. Eclipses. Earth and the Moon, like all other opaque objects that don't produce their own light, cast long shadows into space. When a celestial object partly or completely comes into the shadow of another celestial object, that event is called an eclipse. Josephine, what?
I said, Mommy.
Here.
Mommy,
Earth and the Moon, like all other opaque objects, they don't produce their own light, cast long shadows into space. When a celestial object partly or completely comes into the shadow of another, yes, Jojo?
You done?
No.
You can
Yes, I'm done with that. There is an event called an eclipse. A lunar eclipse. When the moon revolves into the shadow of Earth at the full moon phase, a lunar eclipse or eclipse of the moon can occur. A lunar eclipse doesn't happen during most full moons because the moon's orbit of Earth is tilted about 5 degrees compared to Earth's orbit. If Earth's shadow covers only part of the moon, there is a partial eclipse. The curved shadow of Earth on the moon during a partial lunar eclipse is evidence for Earth's spherical shape. When there is a total lunar eclipse, the moon is completely covered by Earth's shadow, and all people on the dark half of Earth can view the eclipse for up to 100 minutes. The complicated cycle of lunar eclipses results in an average of 2 total lunar eclipses a year. Under rare ideal conditions at the new moon phase, the moon can just barely block out the sun, casting a shadow on Earth that causes a solar eclipse, as seen in figure 4.17. The moon's shadow can just barely reach Earth, making solar eclipses a rare event. A total eclipse of the sun can only be observed at any one location on Earth for up to 7.5 minutes, once every 200 years or so. Question number 743 on page 75, or 74. Why would an observer on Earth see a complete cycle of phases of the moon in approximately 1 month? 1. The moon rotates on its axis. 2. The moon revolves around the Earth. 3. Earth rotates on its axis. Or 4. Earth revolves around the sun. Number 44. If the distance of the moon from Earth were to increase, the length of time the moon would take to complete one revolution around Earth would decrease, increase, or remain the same. Number 45. How does the moon appear to an observer in New York State when the moon is located at position E? 1, 2, 3, or 4. Number 49. In the open ocean, a bulge of water 2 to 3 feet high that follows the moon's movement around Earth is a tide, tsunami, wind wave, or surface ocean current. Number 52. During which event does our moon receive the least amount of sunlight? A Jupiter eclipse, an Earth eclipse, a solar eclipse, or a lunar eclipse? During which phase of the moon do solar eclipses occur? New moon, first quarter moon, last quarter moon, or full moon? And that was your last